Okay, next example. So I want to do the same thing, but for the part of the sphere, that lies above the cone z equals this. Okay, so real quick, if I was to draw this from the side, right? So if I'm just looking straight from the side, I'm going to have a sphere of radius 4. So this is supposed to be a sphere, not a circle, right? So rotate that all the way around. And then the cone x squared plus y squared, or square root of that. So that's going to be a cone that looks like this. I can't draw. Why is drawing so hard today? Okay, so I'm interested in not this region, I'm interested in this surface, right? And not just this line, but kind of, imagine this kind of rotated around the z-axis. So this is going to be z. Oh, sorry, this will be like x or y or whatever, it's the xy plane. It's rotated around, it's going to be the same all the way around. Okay, so here, notice I can't really just solve for one of the variables really simply, right? I'm going to have to do a square root, and I'd rather avoid that because then I start losing out on like negative values and stuff like that. So one thing I can do though is I see x squared plus y squared plus z squared. That should make me think right away about um, spherical coordinates, right? So this is a sphere with radius 2. So let's go ahead and say x equals 2 um, sine phi cosine theta, right? So this is, I'm just putting this into spherical coordinates with radius 2. Y equals 2 sine phi sine theta, and z equals 2 cosine phi. So this is just this equation in spherical coordinates. Okay, but now I can actually rewrite this. I can say r of u and v equals. So I'm going to replace the phi with a u and the theta with a v, just so that way we're consistent with our notation. So sine of u cosine of v I plus the y coordinate, which is 2 sine of u sine of v j plus 2 cosine u k. Alright, so this is my vector function. Now I'm almost done. I need to figure out what is the region of u and v that we're parameterizing over. Okay, so we're going to have phi going from here to here. So I need to figure out what is that angle, what is this angle here, and then we'll be going from negative to positive of that angle. Or I guess, yeah, we'll just be going from 0 to that angle, and then we would rotate this all the way around. So theta, right, we're rotating all the way around the x-axis. Theta, we know, is going to go from 0 to 2 pi. So theta was v, so v is less than or equal to 2 pi and greater than or equal to 0, right? Because we're rotating this all the way around the z-axis. Okay, and then we're looking for this angle here. Okay, so let's set these equal. So we have z squared equals x squared plus y squared. Okay, and then we also have x squared plus y squared equals z squared, so that tells us that 2z squared equals 4, right? Yeah. So z squared equals 2. We know that z is equal to 2 cosine phi. So we have 2 squared cosine squared phi equals 2 cosine squared phi equals 1 over 2, which means that cosine phi equals 1 over root 2. And that tells us that phi equals pi over 4. So in context of our question here, right, phi was the u. So here we're going from 0 to this line right here, which is the line phi equals pi over 4. Right, so this is r equals 2, and this is phi equals pi over 4. And vertical is phi equals 0. So here we're going to have u, which was our phi. I should write that. U equals phi, v equals theta. And that's just so I can have the same notation as in the previous question. Don't have to do it that way, but it makes things a lot easier. Okay, so this is 0. This is less than or equal to pi over 4. So it's kind of similar to setting up, like the triple integrals like we were doing before, except now we're using that to kind of eliminate a variable, right? We're just describing the surface, and we're going to try to eliminate a variable and describe this as just, some region, right? So this surface, right, the top of this sphere that's kind of bounded by this cone, right? I can think of that if I have my u and v coordinates, right? That surface corresponds to some square over here, right? So every point on this square corresponds to a point on that surface. Okay, any questions on this example? So how did I know to do spherical coordinates and not solve for a variable? So here I'm going to try to look for something that looks familiar. Okay, so here I see x squared plus y squared plus z squared. I should think right away, oh, hey, that looks familiar. I can write that in terms of spherical coordinates. If I just had x squared plus y squared, I'd probably think, polar coordinates or something like that. Or maybe y squared plus z squared, I would think polar coordinates. Whereas in this previous question, we just had x by itself, so it was a lot easier to just solve for x. Whereas with this next question, I would have had to have taken a square root, right, to solve for x, or to solve for one of the variables. Really doesn't matter which one. And then I would have been missing a whole, like I would have excluded all of the negative values from this surface, which might not be realistic. So by doing it this way, I'm not actually excluding any values from the surface. So if you're trying to do this in terms of u and v, try not to take any square roots. Prefer polar coordinates or spherical coordinates or cylindrical coordinates even to that. Okay, but one last point is that when we're doing this, so we can convert to spherical coordinates, but it doesn't do us any good unless we actually end up with only two variables. Okay, so we're trying to do this in a way so that I don't have rho, phi, and theta. I want to do it in a way so that I only have phi and theta, or rho and 5 or something like that, where I only have 2 variables instead of 3. Okay. So the next question is, so I have this surface. Um, I have a picture on the next page, so I don't need to draw that. Okay, so here's an example. We have z already solved for, so that's fine. So this is the surface right here, this in blue, and this is the coordinate kind of in the u and v that we're interested in the orange. So now the question is, um, if I take a small little square down here in the orange, how does the corresponding square up on the surface, how does that change? How does the area change? All right, so if I want to do a surface, so I want to find the surface area of this thing. So first, let's write this as a vector function that parameterize the surface. So I have r of u and v equals. So here I could do this just like this. I could just do u I plus v j plus u squared plus v squared k. And this would work, except I'm going to eventually have to switch it to polar coordinates to do this integral. So I'm going to go ahead and do that now instead. So instead of doing u squared and v squared, I'm going to do this in terms of r and theta. Because I see x squared plus y squared, that makes me think, polar coordinates. So here I have r cosine theta. For j, I have r sine theta, j. And then x squared plus, oops, put that back. And then x squared plus y squared, that's just r squared. So this is plus r squared k. So in terms of u and v, because, yeah, I don't want to have all these r's floating around, right? This r is not the same as this r. So I don't want these floating around. So I'm going to write this in terms of u and v. So this is u cosine v I plus u sine v j plus u squared k. Let me put a little arrow over this because that's a vector. Yeah, so I saw the x squared and y squared, and that makes me think polar coordinates. And there's one more thing that makes me think polar here in a second that I'll show you. Um, r equals u and theta equals v. Okay, the other thing that makes me think polar coordinates is that it says lies under the plane z equals 9. So if z equals 9, that means that x squared plus y squared equals 9. And I'm going to be interested in all of the xy values that are inside of this region. Right, so it's kind of describing this circle right here. So again, a circle, I should think this is going to be easier in polar coordinates. So I kind of knew that part ahead of time, or I saw that from the picture. But it also would have been possible to do it the way I did it at first, was just u squared plus v squared. That would have been fine, except when I set up the integral, I'm gonna want to change it to polar coordinates anyways. So you can do it then or now. It doesn't really make that big of a difference. Okay, anyway, so I've converted this um, to a parametric surface, right, in terms of u and v, and I'm interested in the region of u, v inside um, u equals 3. Or actually, let me just put it this way. So to describe the circle, we have u is going to be less than or equal to 3, right? So the radius is going to be less than or equal to 3 and bigger than or equal to 0, right? So the radius goes from 0 to 3, from 0 to 3. And then the theta goes all the way around, right? So theta, the v, is less than or equal to 2 pi and greater than or equal to 0. Okay, so really this parametric surface right here, this surface, we're describing it, it's not really a circle here. In this case, we're describing it in terms of u and v as a nice square, or some sort of rectangle or something, totally not to scale. Okay, and again, every point on this little region right here corresponds to a point on the surface. Okay, so now we want to find the area of this surface. Okay, so to do this, what I need to do is I need to figure out how does a small little area here correspond to an area here? Does it get stretched out? Does it shrink? How does it change? You know, because we're going to be bending it and doing whatever we want with it um, when it transforms from here to here. But how does that area change? Okay, and the answer is actually fairly simple. So I'm going to do, actually let me copy and paste this real quick because that's easier. Um, okay, so if I have my parametric surface, um, so this region here, they're going to call this D. And this right here is going to be my surface S. Okay, so the area of the surface area, is going to be the double integral, so I'm integrating over this region, of the derivative with respect to u cross the derivative with respect to v. They call this the fundamental vector product. And I do the determinant of that. I'm sorry, not determinant. I do the magnitude of that cross product. Okay, so let's go ahead and start computing this. So I have, let's see, let's copy this. Let's copy this down. Okay, so RU, right? This is going to be a vector, and it's going to be the derivative with respect to u. So if I do the derivative with respect to u, this is going to be just cosine v times I plus sine vj plus 2u k. Right, I just did the derivative with respect to u. And then same thing here, rv, it's the derivative with respect to v, so derivative of cosine is negative sine, That's going to be cosine. And then that's going to be 0. Okay, so let's compute the cross product of these. So that's going to be I, J, K. And I have cosine V, sine V, 2u. And then I have minus u sine V plus, sorry, not plus. And I have u cosine V and then 0. So I do this determinant. So first I get 2u, no, minus 2u cosine V, right? So I have 0 minus this. So that's the I component. The j component, remember I put a negative. U squared, you're right. I have 2u and I have a u here in front. So u squared. Thank you, Kevin. Okay, so next I do the j component, so it's going to be 0. And then I'm going to have, so again, it's going to be positive, so it's going to be 2u squared sine v j. And then finally, the k component, I cross this one out and I have cosine squared. So that's u cosine squared v minus minus, that's plus uh, u sine squared v all times k hat. Okay, so I can um, start simplifying this a little bit. So this right here is just going to be u. So I have Ru cross Rv. That's going to be minus 2u squared cosine v I minus 2u squared sine v j plus u k. All right, and now I want the norm of this. All right, so now I want the magnitude of this. Okay, so this is going to be square root of 4 u to the 4th cosine squared v plus 4 u to the 4 sine squared v plus u squared. Okay, cosine squared plus sine squared, that's just going to give me 4u to the 4 plus u squared. And then I factor out u squared, so I get u times, it's going to be 4 u squared plus 1. Okay, and that's the norm of this. So again, they call this the fundamental product of R, or the fundamental vector product. Okay, so what does this actually mean? What this tells me is that if I take a small region here, okay, I'm going to call this d dA. Right, so this is going to be dA. And then I take the corresponding segment over here, right? Because this region corresponds to a segment up here. This I'm going to call ds. I'm going to use a capital S. So how do I relate those two? What it tells me is that ds is equal to this product times dA. Okay, so a small portion of the surface, of the actual surface, when I do the um, parameterization, I get this. So it's kind of like how, remember how when we had for a length, arc length, we had this small segment, and this was actually equal to norm of r prime dt. This is the corresponding thing for surfaces. Okay, so if I want to calculate the surface area, the surface area, integral over S, that's going to be just this, right? I'm adding up all of the small little, segments on the square. So this becomes the double integral over d, and we said ds was equal to ru cross rv dA. And I know the bounds on u and v, right? We calculated those. Those were from 0 to 3 and 0 to 2 pi. So 0 to 3 and 0 to 2 pi of u root 4u squared plus 1 dv du. Okay, so this doesn't depend on v at all, so I can, or it's separable, so I can write this as the integral from 0 to 2 pi dv times the integral from 0 to 3 u root 4u squared plus 1 du. And then to do this, I need to do well, it would be a u substitution, but I'm going to use w instead. W equals 4u squared plus 1 dw equals 8u du. So if I multiply, or I need to multiply and divide by 8. So I have 8 here and multiply by 1 over 8 out in front. And then and then I do the change of transformation. So this is just going to be 2 pi times the integral. So at 0, this becomes 1. And at 3, I have 3 squared times 4. That's 36. This is 37 root w dw. So that's going to be pi over 4 w to the, what, 3 halves times 2/3 from 1 to 37. The 2's cancel. So I get pi over 6 times 37 to the 3 halves minus 1. Okay, so that one was a little bit long. Let me see if I got that right. I think that's right. Yeah. Okay, so this one, it had kind of 2 steps. The first step is to parameterize the surface. Okay, so I want to kind of eliminate a variable so that I can describe my surface as just in terms of 2 variables as a nice little. It doesn't always have to be a rectangle, but um, kind of as this flat region in u and v. Okay, and then after that, I compute this fundamental vector product here. right? So it's the norm. So I do the derivative, partial derivative with respect to u and v, and then I do the norm of the cross product. And then to calculate surface area, I integrate that. But I can also use this to also integrate just regular functions. Um, let's see, how much time do I have? I'm almost out of time. Okay, so real quick, if I wanted to integrate a function over a surface, um, so what that means is I'm going to have f of xyz ds integrating over that surface. Okay, so maybe for instance, this would describe the density of the surface. So I want to figure out what is the mass of the surface. So I would integrate the density of the surface. Okay, but at any rate, the way I would do this is I would write this as the integral, and I would have to transform this into terms of u and v. Ru cross Rv dA. Okay, so every time if you want to do a surface integral of a scalar function, you're going to parameterize the surface so we can find the r. We do this and the bounds for that r, or in terms of u and v. And then we do this cross product and the norm, and then we integrate just like normal. So I'm going to walk through one more. This one I'm not going to integrate a function like this. I'll do that next time. Okay, so it says the part of the surface that lies between x0 and x1 and z0 and z1. Okay, so if um, if I'm looking down, I'm looking straight down. Right, here's x and here's z. Right, so this describes some region, and I have a surface up above this, right? This is my surface. So that's kind of what it's describing. So this one, I'm actually going to do the same thing that I was describing in the first example, where I have r of u and v. So I'll just set x equal to u and z equal to v. So I have u times I plus 4u plus v squared j plus vk. Right, because I already have one of the variables solved for me. I don't really have to do anything complicated. And it looks like this is already going to be a square. Because I know that x goes from 0 to 1, so I have u is less than 1, greater than 0. And same thing for v. Okay, so now I have my parameterization of the surface. Now, maybe I'll find out later on that, it's easier if I convert this to some other coordinates, but I doubt that. But it's totally possible that that could happen. So now I need to compute the derivative with respect to u. So that's going to be, keep the notation. So this is going to be 1i plus 4j plus 0k. And then rv is going to be 0 I plus 2v j plus 1. Okay. And then I do the cross product. Ru cross rv. It's I j k. So we're going to have 1 4 0 0 2v 1. which gives me, so I cross this out, I get 4 minus 0. And then cross this one out, I get 1 minus 0. And then cross this one out, I get 2v minus 0. And minus 0, so that's just 2v. Okay. All right, finally I compute the norm of this. That's going to be square root of 16 plus 1 plus 4v squared. Is that right? That just seems weird that I have... Yeah, okay. Okay, so then the area of this surface is going to be this, capital S, which is the integral from 0 to 1, integral from 0 to 1, 7 plus 4v squared dv du. Okay, and then, so I feel like there might be a mistake here, because if this was 16, this would be a lot easier to integrate. So is there a reason why? So that 1 is supposed to be there, and that 4 is supposed to be there. So I'm just double checking my cross product. So I have 4 minus 0, 1 minus 0, 2v minus 0. Yeah, okay. So then I end up with a not so pretty integral. So this only depends on v, so I can factor it out of the du integral, and what I end up with is integral from 0 to 1 du, integral from 0 to 1, 1 7 plus 4v squared dv. So that's just going to be 1. So whatever this is, it's going to be the integral from 0 to 1, 1 7 plus 4v squared dv. Okay, real quick, I'm not going to work this integral all the way out, but how would I integrate this? Does anybody recognize how to integrate this? Anyone at all? Think back to Cal 2. This is just a Cal 2 question. Integration by parts. So integration by parts, I need the product of two functions. I don't have two functions. Trig sub. Yep, this would be a trig sub problem. Which makes me think it might have been easier to describe this in terms of some other variable to begin with, but I don't really know. It wasn't obvious. So yeah, I'd be doing a trig sub to solve this integral, which I don't feel like doing right now. Okay, so that's the process for finding surface area and for calculating surface integrals. Okay, if we want to compute integral over S, actually I'll just say surface area. That's the integral of this. And then we have scalar surface integral. And we'll be doing something a little bit different for when we have a vector function. Okay, so this is f of u v. D. All right, I hope that helps. Any questions? If not, I will see you guys. See you guys Wednesday. Oh, real quick. So I am caught up on grading the homeworks. I just need to work out with the other TA. There's some problems uploading, so you guys should see those uploaded uh, pretty soon. Anything else? I'll be making videos for the homework solutions and catching up on those and the review. Probably the review is going to come first though. So that'll be either Wednesday or Thursday. Is the, I'm going to say this topic that I just did probably. Um, the I thought he already did. Hold up. Okay. I'm pretty sure he already posted a review. Thank you very much, Kevin. So yeah, he posted the review, and actually, you know what? So I can look at this and see what's on it. So double integral, triple integral, double integral, cylindrical coordinates, double integral of spherical coordinates, line integrals, um, fundamental theorem of line integrals, Green's theorem. Okay, so it looks like it stops at Green's theorem. At least that's where the review stops. So I would be expecting the surface integral stuff on the final, but doesn't look like it's on the review that he sent for exam 3.